Hello, I'm Nathan Jiscoot, a researcher at the TU Delft working at the ISC group, and welcome to my poster presentation. A lot of the things in this presentation aren't set in stone or fully researched yet, but it is better to talk to your peers halfway through than near the end. So here I am. Just in the poster, you'll see that there is a lot of reference to asteroid hydrogenation. That is because we needed to apply our reaction engineering and data evaluation to a reaction. Yet that doesn't mean that any of those two are limited just to only asteroid hydrogenations. They reach much further. For the reactor, we aim to reduce human error. We aim to not have you sit behind your computer again thinking uh, when you're doing your results, is this actually what happened? Is this actually accurate? We want to have a machine that takes responsibility where you would previously. It automatically logs accurate timings for additions and extractions. Um, it adds the reaction mixture, then pressurizes, then adds your catalyst, and then does add automatic sampling, which means that now the start of your reaction isn't a vague moment in time anymore. It is quite defined as the moment when the catalyst was added. This gets a timestamp. All the samples extracted from your reactor gets timestamps. And this means data is more reproducible and more reliable. So with this reactor, we aim to have temperature control, pressure control, and concentration control, all in a six-way manner with six different autoclaves working at the same time, making high throughput accessible to high pressure environments. So this leads to a more interesting type of data, kinetic profile. We have high resolution profiles for concentrations. You'll see this at the top here. And we have even higher resolution data for the pressure uptake, which is the hydrogen pressure that the catalyst uses to convert reactants. These high resolution results allow for more extensive exploration of whatever's in between your initial conditions and your final yields. It allows for all the intricate things in between to be scrutinized. So we do that with data processing. And our first idea was to fit ODEs to our systems because line fitting is currently quite empirical still. You fit exponents or exponentials or anything like that instead of the system that is assumed by all of chemistry, a system of changes based on the changes in everything, which is what chemistry is. So I propose that we fit ODEs to our data. And here on the left, we have simulated some asteroid hydrogenation data. This includes backwards reactions, and then fitted with a system without backwards reaction and a system with backwards reaction. And you see that a system that is more fitting accurately extracts better R squared than a system that is wrong. This is all still simulation, but a first venture into the potential. What we get out of that is not just useless constants A, B, C, D. We get rate constants, actual kinetic constants, K1 to K5, with values that fit our real data best, our data best. Because real data, as you see here on the top right, is still a little bit different. Our systems, assumed systems, have a hard time fitting our real data. But this begs another question. What does our ODE miss? Why can't it fit our data? Are even more interesting questions than just how do we get good fits. So bad fits are not failure, they are also progress. And this opens up a new frontier. We can go from discrete data runs to interpolating them and extrapolating them possibly. Because we get our rate constant. And if we do it at different temperatures, for example, we'll have um, a recreated system that is now fit to our real data that we can just simulate at other temperatures. We can now make a continuous spectrum of everything in between our runs, not only for temperature, but for pressure, catalyst concentration, substrate concentration, generally anything that's in the initial condition. And this, we think, is more interesting than just final yields and just guesswork. A first guess by a computer that helps you guide your research. Thank you for sitting in our progress meeting. If you find the time to talk to me, please do. I love explaining and I love finding your insights about my research. And thank you for listening.